graduate school, Jain University. In fact, Raman is a past student of this department, and I am very proud to introduce him to you all as our alumni of the department. Today he is here to give a talk in connection with the National Mathematics Day celebration to commemorate the birth anniversary of Srinivasa Ramana, which falls on 22nd December 2016. And this is a precursor to that event that we are going to have tomorrow. Raman is going to talk to you all on something related to numbers, curves, and arithmetic. So it's a very rich field that shaped mathematics down since the ages, and it is very much current with lots and lots of abstractions getting into this fertile area of mathematics, and I am sure Raman will be able to kindle that kind of interest all of us who are present over here. I welcome Raman, and before I do that, once again, extend a very warm welcome to him.
I've chosen these three aspects, and then I forgot the Diphantus, the book of Diphantus translated in English by Bashir has got word problems, like so many people were divided into three groups, and if each group had so many people, what was the original number? So they were all word problems, and I doubt, I'm still historically not thorough, I doubt if they were used to writing numbers like 3, 2 or 3. Everything was in words. They were knowing that 2 is corresponding to 2 people or 2 fruits, but the numbers, if you at least some manuscripts that I have seen, they were Roman numbers. So they were handicapped, because this thing that we know so well, they were handicapped with the number systems. So we are so fortunate that nice structure of number line is there. We know these subsets, and we are seeking solutions in subsets. In particular, at a higher level, I want to look at certain discrete subgroups of the real line, which we may call as lattices, and that will help us in geometry. Okay. So, if may I know these are all first year people or second year people? Okay. So at least a little bit of topology is known to you, right? So a lattice is a very special kind of a subgroup of, let's say in this case R. Let's say L is a subgroup of a Lie group G. If there exists at least one neighborhood at the origin of G of L, which satisfies the property that L intersection n epsilon of 0 in G is phi. If this is satisfied, such a subgroup is qualified to be called as a lattice. Okay, and these lattices play a very important role both in number theory as well as geometry because of quotient constructions. Okay, so these quotient constructions come up because this lattice, being a subgroup of an abelian group, becomes a normal subgroup, and therefore G by L makes sense. Okay, so this is just a memory of last week. I was teaching normal subgroups in my class, and I just want to share my experience because I want you also to be as alert as my students. At least in Bangalore, we pick students in a very cautious way. So there are a few students. The moment I told that by default, any subgroup of an abelian group is normal, the immediate question a couple of people asked is, suppose I have a group in which every subgroup is normal. Can I claim that the parent group is abelian? Okay, so it was a naive question. What do you mean by naive? ಮುಕ್ತವಾಗಿ ಬರೋ ಕ್ವಶನ್ ಅದು. ಆ ಥರ ಕ್ವಶನ್ಸ್ ಬರಬೇಕು, ನಾವು ಆನ್ಸರ್ ಮಾಡಬೇಕು. If that naturalness is not there, you are not learning anything. So I want to propagate such kind of thinking in you. And believe it or not, I could not answer immediately because I did not expect that at the BSc level they will ask such a question. And then I came up with a counter example the very next day, that the quaternion group is non-abelian, but all its subgroups are abelian, normal. So I just wanted to say this because whenever you read something, you ask the right questions. Asking the right questions is the right way to do mathematics. Okay, so now we are looking at these number systems, and now when I look at linear equations, you can simply look at things like x minus 1 is equal to 0, x square minus 1 is equal to 0, x cube minus 1 is equal to 0, and so on. Where do they belong? They belong to this polynomial ring. I am looking at zeros in this polynomial ring, and you should be knowing a fundamental result, that all these equations can be solved. We are not searching in a hopeless environment. That is because of the fundamental theorem of algebra. Guarantees a solution. Okay? I think it may look frivolous because all these equations have root as 1, but think of other roots. For example, this has omega square as other roots, which are complex roots. So in general, if I write an arbitrary cubic equation, you may have to resort to numerical methods to find that one real root. In some cases all three are real, and in some cases you have a pair of conjugate complex roots. So that is guaranteed by fundamental theorem of algebra. So once we know that they are there, it's nice to understand the structure of these roots. I claim that there is a nice geometry in this. If you go to the Argand plane and seek for solutions, the first solution is just 1, and because R is not algebraically closed, if I want to go to C, I can see that point as sitting somewhere here. Solution for the first equation. The solution for the second equation will be 1 as well as minus 1. The solutions for the third equation require to go beyond the real line, and so I will quickly draw a circle, and let's generalize it. Even if I say x power n equal to 1, we are trying to look at nth roots of unity, and they are all sitting on the unit circle, because if you look at mod z equals to 1, the graph of this equation is the unit circle. So now it's interesting to know how many of you remember omega? I vaguely remember it. it's half plus or minus root 3 by 2 or something like that. No? Okay, let's do it. So we are trying to solving equations is equivalent to factorizing, right? Because we know that 1 is a root, let's factor it by x minus 1, right? So the quotient is x square, yeah, minus 1 minus x square, so wait, x square minus x square minus 1 plus x square plus x it's minus x. Wait, x into x square is x cube minus x square plus x is x square minus x. Sorry, yeah, thanks. Minus 1. So now, yeah. So your quotient is x square plus x plus 1, right? So your roots are omega equal to minus 1 plus or minus root of b square is 1 minus 4 divided by 2. So it is minus half plus or minus root of minus 3 by 2 is minus 1 by 2 plus or minus root 3 by 2 times I. Yeah? Yeah, this is your omega. Right? So if you see properly, it is at 120 degrees. If you draw it in the Argand plane, it is cos 120 plus I sin 120. Okay? So the other root minus is fortunately group theory applies and it is omega square. So you get something like this because it's symmetrical. And the trivial root is 1. Right? So we could see an equilateral triangle sitting on the unit circle. So this is the first instance where you see cyclotomy. Circle is cut into 3 equal arcs by 1 omega square. And this beautifully generalizes to this equation as well. Pick any n, let's say 7th roots of unity, it divides circle into 7 equal arcs. 10th roots of unity, it divides circle into 10 roots. Okay? And see, it's so nice. Unit circle is 2 pi, it's irrational. Irrational is nicely cut into equal divisions.
Even is not an issue.
Huh?
N even is not an issue. N odd is an issue.
Meaning, I didn't get.
Which ones are constructible?
Yeah, in the sense of constructible, yeah. So, this is the first instance where I see arithmetic coming up right from something at the school level. I'm sure this is a problem at school level. You would be solving quadratics at the school level, right? So, now we could go to easily, we are led into the second part. We can look at curves. And the moment you think of curves, what comes in your mind? Probably more memorably etched in your mind is things which you have sketched practically, like a cycloid is sketched, right? A diamond shaped curve is sketched. But unfortunately they are not algebraic, meaning that their equations cannot be solved in such an easy manner. They are transcendental. So you have to resort to numerical methods to find. That's why curve sketching has got so many rules to perform to see where this curve is existing. But I am focused on curves defined by polynomials. So again, let's say polynomials in two variables. Polynomials in two variables they are belonging to kxy for k an algebraically closed field. I mean,
They should be told what is algebraically closed.
Oh, okay, fine. Just now we said that an equation like x cube minus 1 is equal to 0 has got only one real root. The other two roots we had to go to the complex plane. I can write some equations where you will not at all get real roots at all, which means which is the ideal playground where I can search for roots. Yeah, the fundamental theorem of algebra says if you enlarge your domain to the whole of complex plane, I am definitely guaranteed to get a root. Right? So such fields are called algebraically closed fields. And now I am reminded that probably you may not be well versed with fields. Please read Rudin. The very first few pages, he has beautifully explained fields without resorting to rings, integral domains or whatever. Okay? So you have axioms A1, A2, so on. You have axioms M1, M2, so on in Rudin. If any number system satisfies them, it is a field. In a very simple manner, a field is something which freely allows you to do plus, minus, multiplication and division. A field is any number system which freely allows you to do plus, minus, multiplication and division. Okay? And you never questioned this in the school, because I know even my teachers used to teach me all these four things, and there was never a problem that in this number system this is a problem, because we were given easy. For example, when division was given, they were giving easy problems where they were exactly getting divided. Okay, so we never came across this difficulty. But otherwise, if you say divide 7 by 2, then they used to add some clumsy things like there is a remainder, there is a quotient and all that. But actually, it is not perfectly divisible. So this does not belong to Z, right? So where does it belong then? It belongs to Q. So if you enlarge your domain from Z to Q, now your division problem is solved. Except there is one small problem. You can't divide things by 0. Okay, that thing is taken care by the field axioms itself. Field axioms say division is possible everywhere except by 0. So if somebody has learnt enough of ring theory, if every non-zero element of the algebraic structure has a multiplicative inverse, that's enough. I am not imposing invertibility of 0. That is absurd. Except 0, rest all should have multiplicative inverses. Okay? So let me remind you one more thing. When we do in schools, when we factorize in schools some quadratic equation, let's say x square plus 5x plus 6 is equal to 0, when I say it is x plus 2 times x plus 3, I immediately say this implies either this should be 0 or this should be 0. You know, implicitly I am assuming that I am working in a integral domain, because you can't have product of two non-zero elements to give 0. One of them has to be 0, right? But in Z6, do you see 3 times 2 is 0 in Z mod 6, right? So implicitly we are also doing our calculations in integral domains, and thankfully all my number systems in R, because R is a field, this integral domain property is inherited by all the subsets of R. So we are safe. Okay, so I think that was a small deviation back to number systems, but okay. So now when I say two variable polynomials, the best thing that you can say is y is equal to mx plus c. What you are doing in school is defining a two variable polynomial, right? Yes. Now you might have plotted many of them in your schools, correct? Now let us impose m belongs to q. So y is equal to some p by q times x plus some c. Now does this automatically say something about the points on which this will travel? If m is rational, does the line always pass through rational points? The question. Let's think about a simpler case. Y is equal to mx. I mean, it's a naive question. Even I myself don't know. I've just put up the question. So, can I expect an ordered pair x1, y1 to be a solution of this line where both the components are irrational? Okay, so irrational. Okay, so if I put x1, y1 in this place, y1 is equal to mx1 implies y1 by x1 equals m. And can I have numerator irrational, denominator irrational, but this is a rational number?
Pi by 2 pi.
Yeah.
Root 2.
Yeah.
It can also.
Yeah.
The thing is, you can't do the other.
Yeah.
You can't have. I mean.
No. Can we conclude something?
Is true. If one of them is a rational number, the other will also be a rational.
Yeah. That's what you wanted, right?
No, I was really naive in putting this question. Okay. So now I can conclude something. If this were to be an irrational ordered pair, then they are proportional by a rational.
What is the intersection there?
No, but I mean, what?
If I want to impose that there is an irrational ordered pair, then
both the coordinates are
irrational, then they should be related by a rational proportion, and that is exactly this.
Yeah.
I mean, you can cancel off the irrationalities and get a rational number.
And I do not know what you mean by irrationalities, but the thing is that is always true, because I mean, take any rational pair, what you call, they always line passing through the origin and that point. That is always of the form y equals mx.
Yeah. Okay. So
the thing is, why should m be a rational number?
I am imposing it. That's the condition for
Why should
it.
m be a rational number? That is the question that is to be asked.
No, but see. Now this is a continuum. This is a continuum. This line is a continuum. Okay.
What continuum?
Continuum in the sense
I mean,
it is homeomorphic to the real line. It's homeomorphic to the real line. Okay. So which means if I divided it by all rational points, there will be gaps in them, and they have to correspond to irrational numbers.
What is objectivity? some form variance of
Yeah.
Archimedean.
Archimedean is all about real line, and I have gone into R2.
That m is a rational number because for all rational x's, your y's will be rational number, because I mean that should be true for every y1 and x1.
Yeah, as long as
it's also true for rational x1. So your y1 will also be a rational number. So y1 by x1 is always a rational number. So m is always a rational number.
So, yeah.
There is something they call Dirichlet theorem is something to do with rationals and irrationals simultaneously.
This is in which domain you are speaking? Dirichlet theorem is?
Dirichlet is a deep
Result in what area?
in number fields. Okay.
Okay, I don't know.
Yeah.
Okay.
You are trying to probe that kind of a situation only here.
No, I am unaware of it. I am unaware.
Basically, you are trying to solve an equation, right?
Yeah.
The moment you go to quadratic,
Yeah.
these things will come up more naturally. There you can really see. That's how real numbers are defined as the limiting sequences of rational.
But this is a very easy case. See, ax plus by plus c is equal to 0 has infinite solutions. This is the fact. The straight line has infinite solutions. My claim is,
Yeah, you are looking at right?
my claim is this set. Let S is equal to set of all x, y such that ax plus by plus c is equal to 0. This is literally the graph of ax plus by plus c is equal to 0. My claim is S has a group structure. Okay. Now, how many ways you can look at? One, full S. Second, W, a subset of S, which is equal to where W is set of all x, y such that ax plus by plus c is equal to 0. In addition, x, y are rational numbers. I want to put a constraint that they satisfy this equation, but they are also rational. Okay, I can put one more, V subset of W subset of S, where these points x, y are such that x comma y belongs to Z. So I can categorize. These are the set of all real points, set of all rational points, set of all integer points. Okay, so I want to look at the structure of these things. So
This Jain sets a shrink that you get infinitely many integers.
depends upon my equation. Yeah. So there is a theorem. V is non-empty if and only if GCD of AB divides the GCD of A and B should divide C. Only then I can get some points, otherwise I can't get. Okay? So this is the number theory result, very elementary number theory. Yeah. I think the first course in number theory that you are learning will have this theorem. I have put it in a geometric sense. It's up to you to decode it and see how it is put in Baker or whatever book you are following. It is there. Okay. Next, I want to simplify it for the case y is equal to mx. This is easily seen. If I don't have I can always bring this to y is equal to mx plus c, right? But if c is 0, then this theorem is trivial because any number will divide c, right? I want to have a particular case where c is 0. If c is 0, it is ax plus by is equal to 0, implies by is equal to minus ax, implies y is equal to minus a by bx. So it is y is equal to mx, right? Now in this case, every solution is of the form x1 mx1. This is exactly what is my S in this case. Choose x1, the corresponding y is mx1. Make sense? Make sense? For example, because in this, if I say mx1 equal to m, in place of x I am putting x1. So it is satisfied, right? So every x1 mx1 will satisfy this equation, correct? So let me picture this. This theta where theta is tan inverse of m. Okay, 0 0 is a solution to this equation. I claim that is the identity element of this group. 1 1 is a solution of this equation. 2 2 is a solution of this equation. 3 3 is a solution of this equation, and so on. Anything in between also, right? Now, how do I get this from these two? 1 1 plus 2 2 is equal to 3 3. Just add them component wise. That is your group law. So, in a very trivial fashion, I am showing a group law on y is equal to mx. Challenge is to translate it to a line like this. I am happy to see that this question arose in me. I asked some experts and they immediately said, yes, you can transport this group structure to this line by this change. What is this? A change of coordinates will give a new origin. That ordered pair is your identity element. Yes. And you can expect the same law, but it is not that simple. It is not just coordinate wise addition. Okay, so I can give a reference of my paper where I have given the group law. There is a group law for this line. Instead of y is equal to mx, if I go to y is equal to mx plus c, I have explicitly given the group law. Okay, so we can see avatars of this in a different setting also. Again, we'll go to x square plus y square is equal to z square. This is a equation in 3 variables. What do integer solutions of 1 indicate? What do rational solutions of 1 indicate? What do real solutions of 1? This is my question. Any answer? Your famous triad 3, 4, 5 will satisfy this? What can you say about 3, 4, 5? It's a Pythagorean triple. So, integer solutions of 1 are precisely Pythagorean triples, and rational solutions of 1 can lead you back to integer solutions. That is the question, that is the thing that you can ponder about. Rational solutions can also cook up integer solutions. Okay, so let us see again how geometry and groups get interlinked to this. So rationalizing 1 or normalizing 1, we can get x by z the whole square plus y by z the whole square equals to 1. Correct? So now whether x and z had rationals or integers, this whole thing is again a rational as long as z is not equal to 0. Okay, provided z is not equal to 0. But now if I give a new variable to this as capital X, capital Y, again we come back to the unit circle, right? So see, nice linkages of arithmetic to analytic geometry. You all studied this circle so many times, right? So how do you see 3, 4, 5 on S1, the unit circle? This is the question. 3, 4, 5 is leading to this. How? So let's see. 3 square plus 4 square is equal to 5 square. This implies 3 by 5 the whole square plus 4 by 5 the whole square equals 1. So the Pythagorean triple 3, 4, 5 leads to a solution 3 by 5 comma 4 by 5 on the unit circle, right? So somewhere in the first quadrant you have 3 by 5 and 4 by 5, right? So now like that you can look at all kinds of points here, and we want to know the arithmetic of this, correct? So in a very simple manner, what are the easiest solutions? 1 plus 0, 1 square plus 0 square is equal to 1. So 1 comma 0 minus 1 square plus 0 square is equal to 1. So that will be what? Here. Yeah? 0, 1 and 0 minus 1. Right? So what I did initially, what was that? 1 minus 1, the same thing is coming here again. That was the solution for x square minus 1 is equal to 0. Right? So I indicated that all xn is equal to 1 ultimately will come to the circle. So this also comes to circle, this also has come to the circle. Now let us go to x power 4 equal to 1. What are the solutions of x power 4 equal to 1? I minus I, 1 minus 1. In Argand diagram, how it looks again, it looks like the same way. This is 1, this is I, this is minus 1, minus I. So you are seeing a mirror image of these 4 points in 2D geometry to the 4 points in complex plane. This is isomorphism, right? We are isomorphically looking at two groups, both of which are solving something related to the circle. Now comes a question: how many of you have studied group theory seriously?
Seriously.
The point is, somebody who was who is seriously doing a group theory lecture should at least make you familiar with the common heroes. If you are familiar with Bollywood, you know the reigning stars are Ranbir Kapoor, blah blah blah. Like that, somebody who is teaching group theory will say basic groups, right? Cyclic groups. What are all the cyclic groups of order 3, order 4, order 5? You should be knowing. You fix order 4 because there are 4 points. How many groups are there? There is a theorem that there can be only 2 groups of order 4. One is the Klein 4 group. Up to isomorphism, there are only 2 of order 4. This Klein 4 group and Z mod 4. This is cyclic of order 4, this is non-cyclic of order 4. And both are abelian. My question, this corresponds to this or this? It is something like Ranbir Kapoor has come in a disguised form, you should identify whether it is Ranbir Kapoor or not. Identify. Okay? Now you see, I have already given you a hint that it is like 1i minus 1 minus I. Okay? Now try to see. I square, I cube, I power 4. It is generated by one element. Any group which is generated by a single element is cyclic. So this has to be this. Okay? The point is, you are reading reams and reams of pages, you are not identifying with pictures. It's very much there right from your second PU days, in front of you, but you are not identifying them. That's the big question. Okay, so I showed you the triangle group there, I showed you the 4 element group here. It's up to you to look at 5 element group, 6 element group on this. You can look at them. Please do the computations. Just like I showed you, omega is actually minus half plus root 3 by 2i. You compute other roots where they are located. It's no big deal. They are very much on the Argand plane. And your PU teachers have made you struggle so much. So you can anytime go. Right? You have struggled so much with your second PU exercises that it's effortless play for you. Now if you want to go back to second PU exercises, you can always identify where it is located. So nth roots of unity can always be located by you. It's a nice exercise. Play the game. Enjoy mathematics. Okay. So that is about the 4 element group on the circle. Can I also give you the group law just like I gave on the line? Do you want me to give the group law on the circle? Yes? You have an aspiration to see that? It's very simple. Any point here in the polar form is e raised to power I theta. By Euler's formula, this is cos theta plus I sin theta. Right? What is theta corresponding to this? It is the angle made by the line drawn to the origin. That is the radius vector. Right? So this is the unit circle. Radius is 1 and you have theta. If I say what is this point, you can find theta. Right? So when I said 3 by 4 and what was that point? 3 by 5 and 4 by 5. You can correspondingly find some theta 1 where it lies. Right? So like that for any point you can find a theta. Let's say this is theta 1 and this is theta 2. Here is to I theta 2. Right? Just like I said, the point x1 mx1, x2 mx2 in the line, like that you have v1 and v2. I want to find a v3 which corresponds to the sum of v1 and v2. Do you want to know how to get it? Simply add theta 1 and theta 2. This has to be ei theta 1 plus theta 2. Do you know why? See, this is cos theta 1, okay, I am multiplying e raised to power I theta 1 times e raised to I theta 2. This is cis theta 1 times cis theta 2.
This is a trigonometry.
Yeah, it's trigonometry. By trigonometry, after expansion, you will come to know that this new complex number is precisely cis theta 1 plus theta. And that is the binary operation. Right? What is the inverse of, let's say, this point? What is the inverse of cos theta 1 plus I sin theta 1? Cos, let's say, minus theta 1 plus I sin minus theta 1. Or in other words, it is 2 pi minus theta. Right? So, it is antipodal points. And by this logic, the rule is cis theta 1 plus star cis theta 2 should be equal to cis theta 1 plus theta 2 equal to cis theta 1 plus minus theta 1 plus cis 0. Which is the point corresponding to cis 0? So that is your identity element. While this is your inverse, this is the identity element. Right? And because these are all complex numbers, we know that already complex numbers have a group structure. Associativity is true. Commutativity is true. So this group is an abelian group. Right? And how many points are there in this group? As many thetas are there. How many thetas are there?
As many points.
Infinite. 0 to 360 is not only 360 degrees. I can have 1.5 degrees. I can have pi by 2. I can have pi by 3.
For every real theta.
For every real theta. Theta. Zero to 2 pi is an interval on the real line. Any interval on the real line has got infinite points. What kind of infinity? Is it countable or uncountable? They are uncountable. So this group is uncountable. I showed you 2-element group. I showed you 4-element group. I showed you an infinite group with uncountable elements. It is a Lie group. It is a Lie group because it also has a manifold structure. Circle is also geometrically a manifold. So it's a Lie group. And interestingly, these are obtained by pure algebra. I told you real line. I told you integers is a subgroup of real line. Because it is abelian, we can have normal group. R by Z, by a nice construction, is isomorphic to S1. This circle group can be realized as quotient group of the real line by Z. Forget all trigonometry, forget all these things. Simply as a quotienting procedure, you will get the circle group realized as a quotient of R by Z. And now comes a theory. This can be generalized. R is a trivial Lie group. Z is a lattice. Whenever you quotient a Lie group by a lattice, you will get such nice symmetries. You will always get a Lie group again. I mean, it has group structure as well as a nice symmetry. Okay, so I gave the entire scenario. What are nice subgroups of them? Which of some of them I have already given you. One is a 4-element subgroup. See, just like in the whole real line which is infinite, I can just pick integers and that also forms a group. I can only pick rationals, that also forms a group. But you don't have a finite subgroup of real line. Do you have a finite subgroup of real line? You don't have. But here, the parent group is infinite, and you have finite subgroups. This is interesting. That is very trivial. Only subgroups of real line are Z, Q, and then extensions of Q. But they are all infinite. But here you have got uncountable group, countable subgroups like rational points, and also finite groups like 4-element group, 5-element group, 6-element group. Name a number, you will get. You tell me 100, I will get a 100 group, element group. You tell me 1000, I will get a 1000-element group. Anything is there in it. So it's a very rich structure. Okay? So identifying subgroups of S1 is a nice project. I am told that sir tries to give you assignments. You pick up such nice, very elementary problems. Your teachers will be happy. When I also give assignments, people will say some application in coffee machine, calculus is used, blah blah blah. They will try to connect mathematics. Maybe there is some mathematics, I don't deny it. But there is such an essence in pure mathematics also. You are trying to go into some machines and try to find mathematics with a lot of hardship. Effortlessly you will get some nice, interesting scene here. Try to take such easy exercises. It's nice. So I end my talk here. This.
See, Ramana. Thank you so much. Any questions? Yeah, I was very happy to see that I was into number theory, otherwise I was a geometer. My talk may take further into these excursions, and I'm very happy to see that Raman gave a very good start, and I'm sure you must have all enjoyed it.